Good day to you. In this module, we're going to be talking about how materials deform under forces. And physicists have some very precise ways of speaking about this, in part because it helps analyze and normalize the vast range of different kinds of materials and shapes that are out there. So just let's begin by talking about how it is that objects deform under forces. And we've done this before in another module, but let's just refresh our memories here. If we have an object like this fanoodle from a swimming pool, we can make it change shape if we put forces on it. And of course, I'm applying the forces with my hands. And these forces come in multiple different varieties. One is if we pull on either side of it, we lengthen it. That's called a tension force. If we compress it from either side, that is, put a force inward, that's going to be called a compression force. We can also have bending forces, and as you can see, if you bend it, the length of the object changes as you bend it. You have twisting forces, which are called torsion. And all of those, in all of those instances, there's a relationship between the amount of force that you apply to an object and the degree to which it can be deformed. Well, physicists have a special way of thinking about that, and the way they have developed is to define precisely two quantities that are related to one another. One is stress and the other one is strain. And we tend to use those terms interchangeably in the vernacular. We can say we're either under a lot of stress or we're taking a lot of strain. But in physics and especially biophysics, those two terms have very, very precise meanings. So let's take a look at what those meanings are. First of all, we're looking at kinds of deformations that are elastic deformations. And when we refer to an elastic deformation, we're referring to a kind of deformation that results in no net change of shape of the object. So that if we take a cylinder, for example, and we put a tension force under it, that is, we pull it one way or from both ends, this cylinder will deform, it will get longer under that force, and it will also tend to get thinner under that force as well. Now, the degree to which that stretching will take place will be dependent on the force. And the first thing we can do is we can define precisely this quantity strain, which is part of this. And to do this, we just measure the length of the object that is not being stressed, and we'll call that L sub 0. And then we come along, once we've put it under stress, and the new length we will call L. And the strain is the proportional change of length with respect to the original length. And so strain is usually abbreviated with an epsilon, and we can put a very simple equation that describes strain for us. The strain is the strained length over the unstrained length. L over L sub 0. And there are a couple of things to notice about this term. The first thing is that it is a dimensionless term. The units that are associated with length are meters. The units that are associated with the unstrained length are also meters. And of course, as we've seen before, units can be treated essentially as quantities. And so meters cancels meters, and this is essentially an undimensional or dimensionless number. Now, when we have an elastic deformation, if we release this strain right here, if we release these forces, this object will spring back to its original shape, and when that happens, that's called an elastic force, or elastic deformation. Okay, now that's the definition of strain. What about the definition of stress? Again, that has a very specific definition as well. If we put this object under a certain force is pulling this way, and it's pulling this way, that force is going to be acting throughout the length of our object. And if we take our object here, Here's something that we can strain. We can put a force on it under, let's say we're putting a tension under it. The force that we're acting on the ends is going to be the same as the force acting in the middle and all along the length of this. So what we can do is we can say that the same forces that are operating on the ends are also operating on an imaginary disk right there in the center. And if we cut that through, then we'll end up with an area, a cross-section area of material. And in this case, it's going to be the area of the hexagon minus the area of the hole in the middle. And so what's happening there is that the force is acting across a cross-section area of the object. Now, force, of course, is given in units of newtons, and the force is acting across a cross-section area of the object. And we see here kind of an interesting thing. This has units of meters squared. And if you look at what the units of this force are, then this is actually equivalent to a pressure. A pressure is a force acting over a certain area. And so the forces acting on this object are actually the force over the area. And this has units of pressure. That is, in the SI units, this quantity here, this ratio of force over area, is actually a pressure with units of pascals. And this force acting across an area is the formal definition of stress. Now, stress is usually abbreviated or symbolized with a Greek sigma, and the stress is actually the force over the cross-section area of whatever object that it's operating through. And this means that therefore the stress is formally a pressure. All right, now let's take a look at what happens with certain kinds of things that are under stress and strain. And one of the things that we can do is we can actually plot the degree of strain on an object against the stress of that object. And it stands to reason that if I take this object and I pull on it a little bit, then the deformation won't be very great. If I pull on it a lot, then the deformation will be greater. With most materials, most physical materials, and we're talking here about springs and metals and woods and those kinds of things, there's a very nice linear relationship that exists between stress and strain. And that linear relationship is embodied in a number that is calculated from the slope of that object. And this is symbolized with an uppercase Roman E. And this quantity right here is known as Young's modulus of elasticity. And Young's modulus of elasticity is the quantity that gives you the relationship between stress and strain in any kind of an object. Now, it's important to realize a couple of things about Young's modulus, and that is, one of the most important is that the Young's modulus is a property of a material and not so much of an object. This means that if you have an object with a cross-section area that looks like a circle, for example, and this could be a circular rod, and you compare that with something that has a hexagonal cross-section with a little hole in the middle of it, like our fanoodle here, or you have some kind of complicated cross-section shape here with holes scattered various places in through there, the same curve will describe the relationship between stress and strain in all of those. Now, we're going to come back to the effects of shape and size in another module, but the important thing to realize here is that the Young's modulus is actually a property of a material rather than of an object itself. Now, some things about the way Young's modulus behaves. Obviously, it's going to vary. And if you have, for example, a very, very stiff material over here, and we've described in red over here, you're going to get a large change of force for a small change of deformation. When you have a large Young's modulus, that corresponds to a stiff material. If you have a small Young's modulus, you get a large change of strain for a small change of stress, and this describes compliant materials. This, for example, could be like a rubber band. This could be like a steel wire, for example. And so the magnitude of the Young's modulus is directly proportional to the stiffness of whatever material that you're looking at. Okay, now this is a physics of life course, and so let's just wrap up with a little description of the different kinds of Young's moduli that you can expect to see amongst different kinds of materials. And so what we're going to do is we're going to just make a little table here, and we're going to start down here at the bottom. We're going to start with steel wire, and this obviously is going to be a very, very stiff material. And if you measure the Young's modulus, then you're talking about a Young's modulus of about 200,000 megapascals. Keep in mind that the relationship is between stress, which has units of pressure, and strain, which has no units at all. Therefore, the units of Young's modulus are the same as the units for stress. That is, it acts as a pressure. And so obviously steel is a pretty stiff material, as we would guess. And fortunately for us, bridges are made from steel, and that's a very good thing because that way our cars won't fall off the bridges. There are some biological materials that are very, very tough. And if you look at the Young's modulus of teeth, for example, you find that it's not quite as stiff as steel is, but it's still right up there. The Young's modulus of teeth are on the order of about 60,000 megapascals. That's very, very stiff. If we take a look at the stiff materials that comprise our own bodies, namely bone. Bone is right up there also. It's a very, very stiff material, and this has a Young's modulus of about 18,000 megapascals. If you look at the things that connect muscles to bones, this could be tendons. Oops, I meant to write a T there, not an F, so we'll get rid of that. Tendons, the things that connect muscles to bones, those are actually much more compliant than bones are. We're looking at a Young's modulus of about 1,500 megapascals. There's another stiff material in our body which makes up our earlobes and our noses and all kinds of other structures. This is very important also in the embryological development of bones. That's cartilage. If I wiggle my nose back and forth, what I'm doing is I'm deforming cartilage in there. Same thing if I wiggle my earlobe back and forth. And as you can expect by the ability to actually change the shape of the nose quite dramatically with small forces, that has a very small Young's modulus. That is a very elastic tissue. And then when you start getting into other kinds of animals, the sea anemones, I'm sure any of you who have been to the beach have run into any of those, and if you touch them, you see that they're quite squishy little creatures, and if you measure the Young's modulus of those animals, then you find that they're about 0.1 megapascals, or about 10 kilopascals. Okay, so this is the range of Young's moduli, not only of physical materials here, but also of a range of biological materials. And you can see they vary quite widely from fairly squishy, soft tissues up to quite stiff tissues like teeth. Okay, well that's all for now, and in another module we're going to be talking about fun things you can do with the relationship between stress and strain. Good day to you.